Hello, my name is Jan-Ketil Rød, and I will in this video continue to talk about representation, this time with an emphasis on raster data. Most of the content of this video is taken from chapter 2 in the book GIS Tools to Understand the World. For vector data, there are three geometries available for discrete objects: points, lines and polygon, and the point is the minimum unit. For raster data, we do not have discrete objects. We have a grid of equally distributed grid cells or pixels, as shown in the illustration. The word pixel is short for picture element, and for raster data, the pixel is then the minimum unit. Each grid cell or pixel has one value, and you can code the pixels as belonging to a certain category of points, lines or polygons. However, more common it is to use a raster to show continuous phenomena. Continuous means that the phenomena is everywhere. There is a set value for any location. And this is showing an example: elevation or height above sea level. This is something which we find everywhere. And this shows then an elevation model for one watershed in Trondheim. And we call such a raster a DEM, short for digital elevation model. And this also shown then a zoom in of this digital elevation model close to a place called Steinan. And if we use the identity tool in QGIS and click on this pixel here, we get up the pixel value for these grid cells. And as shown here, there's only one value for each pixel. We have different types of rasters. Typically, these are divided into either image raster or thematic raster. Image rasters are those rasters produced by an optical or electronic device, such as a camera or a scanner. Aerial photographs, satellite imagery, those are image raster. And also, if you have a scanner and scan a paper map, the resulting image would also be an example of an image raster. Image raster are often used as background for visualization purposes, but sometimes also used for analytical purposes, but then they need to be processed further, be used analytically. The second type of rasters are the thematic rasters. These represent geographical features or phenomena, and we can have either discrete or continuous types of thematic raster. Whatever type of rasters you have, we only have one value per pixel. Raster images, such as aerial photographs or scan maps, could be combined with other maps if they are georeferenced, but to be used analytical, we need to process them. And the upper right image here is showing a scan map, and the bottom here the result after it has been transformed into a polygon layer. Norge I bilder, or Norway in images, is the web portal for viewing and downloading satellite imagery and aerial photographs for Norway. In order to download imagery, you need to be logged in, and then the export dialog is available. Not everyone can get a user, but if you study at a Norwegian university, there should be one contact person with login privilege at your study site, which can help you with downloading imagery. For the menu here right, it has an entry for satellite imagery and aerial photographs. And what is called aerial photographs here is orthophotos. That is aerial photographs which have the properties of the map, such as a uniform scale throughout the image and an image that is georeferenced. That means that aerial photographs downloaded from Norge Builder, you can use it directly in any GIS. You will notice when opening an aerial photograph or satellite imagery in a GIS that they have 3 bands. Images can use various parts of the electromagnetic spectrum, but optical sensors taking pictures in the visible part of the spectrum will produce images that shows what we are also able to see with our eyes. So each of the 3 bands have pixel values for the reflection received from 3 sections of the visible spectrum. So the red band is showing then a raster with the reflections from the red part of the visible spectrum. The green second band shows pixel values for the reflection in the green part of the visible spectrum, and the third band, the blue band, shows then a raster with pixel values of the reflection in the blue band of the visible spectrum. And these 3 bands are combined to produce what we call a true color composite, and the image resembles what we would see with our eyes. 3 bands are needed for raster images to have colors. 1 band for each of the parts of the electromagnetic spectrum, and when we combine red, green and blue colors, we use the red, green, blue color model. This is a typical symbolization available also in QGIS when you symbolize a layer. And commonly 8-bit is available for each of the band, which means that the values range from 0 to 255. Combining 256 different colors for 3 bands means that there is more than 16 million combination and thus more than 16 million colors available. In QGIS there is also a 4th band available, a bit confusing as it has nothing to do with infrared radiation or any other parts of the electromagnetic spectrum. In QGIS you can use a mask to clip a raster, and for this image I have used a watershed to clip the image, and then the mask ends up as a 4th band called the alpha band. I'm going to demonstrate this in QGIS. Here is then QGIS open with the imagery, the aerial photographs, and if I use the identify button and click somewhere inside the watershed, inside the area for the Leirfoss imagery, I will see pixel values for the 3 bands constituting the image and also for the 4th band constituting the alpha band. Now these are then the 3 bands and the values of the red, green and blue, which produce the color composite and the color for this particular pixel. If we, however, clip outside of the imagery, all 4 bands has 0 values. If we click outside the extent of the imagery, we will have no data because it's outside of the extent. So when the alpha band is present, pixels that are within the frame of the square are displayed transparent. If you need a raster imagery, this is an overview of 3 places where you can get one. And these are QR codes for 3 different YouTube videos demonstrating how you can download these data. This was the end of the image raster. So the second type of raster was thematic rasters, and these can be either discrete or continuous. Discrete data typically represent objects that have known and definable boundaries, like buildings, land parcels, and cultivated land areas. It is easy to define precisely where the category begins and where it ends. And in this illustration, each cell is assigned to a particular category, such as forest, urban area, and there is a distinct boundary between these areas. Discrete thematic rasters were common for land use categories at this scale in the early days of GIS, since most GIS then were raster based. Today, vector data is dominantly used for discrete topics at this scale, but discrete thematic rasters are still common for global data. Global data set of forest resources from the Earth Resource Observatory and Science is shown here, with a little subset of the global data set showing the forest resources in Congo and nearby countries. The resolution here is 1 kilometer. That means that each pixels cover a ground equal to 1 square kilometer. And this data set is having 5 classes plus 1 class for pixel not being classified. So those dark green pixels are representing closed forest, and the lighter green are representing open and fragmented forest. Now this is an example of a discrete data set. That means that the pixel values are integer. Only 6 different values are here, so values 1 up to 6, and with discrete data set with integer values, we can have what we call a value attribute table, or sometimes called a raster attribute table. And this is then shown here. It shows then the pixel values in one column, and there is a second column showing the count, how many pixels has the given pixel value. So in this data set there are more than 40 million, almost 41 million pixels having the pixel value 1. Not always, but you can also add a third column, which is could be a label describing then the pixel values. More common for thematic rasters is that they are representing a continuous phenomenon. Continuous data, for instance surface data, represent geographical phenomena that can vary at every location, such as elevation, temperature, etc. And here we do not have integer. Normally this is float values with many decimals. Here we only show the first decimal, and then potentially each cell in a raster, in a continuous raster, can have different value. So we cannot have a raster attribute table or a value attribute table for continuous thematic raster. Important for raster is how they can be located. So I said for image raster you download from Norge I Bilder. This you can use immediately in any GIS because they are referenced. They have the properties of the map with coordinate system information. But if you have a scan map, it's very likely that the raster is not georeference, and then the rows and the columns are used as reference system. And the upper left corner is the origin then, denoted by row 0 and column 0. We start counting with 0. So one particular cell would have then the coordinates related to the cell origin, the row 2 and the column 1. I'm going to demonstrate an issue about locating grid cells and have therefore opened QGIS showing a map of the countries of the world. Now I have a scanned image of ethnic groups in Africa south of Sahara, and I'm going to add this image to the map. What is showing here is just a very small part of the raster image. If we zoom out, we see that the raster image, the scan map of Africa, is very poorly aligned with where we are supposed to have it with the rest of Africa here. Now, why is this happening? So let's try to explain it. We have a map layer in geographical coordinates. That means that origin is where equator crosses the Greenwich meridian, about here. The raster image is a scan map and the coordinate reference system is unknown. And then it is the upper left pixel, which is the origin, which is denoted the 0, 0 location. Now we can also know that this raster, it has these numbers of columns and it has these numbers of rows. So more than 7,000. When adding then the image to the map, where the extent of the east-west direction is from minus 180 up to plus 180, then this image with more than 7,000 columns will totally go beyond the extent of this map. So in order to show a scan map together with other mapped feature, you need to georeference the raster. The details about how to georeference the raster will not be provided in this video, but this illustration shows what is needed. On the left-hand side is the image coordinate system with a raster with column and row reference, giving a location for a particular cell with its row and column reference. And this needs then to have a connection with the map coordinate system, locating the C, whatever is here, with coordinates from the coordinate system. So there needs to be established a link between what we call the image coordinate system and the map coordinate system. Now when this link is established, we have a georeference raster, and very often after a raster is georeferenced, it seems to be tilted, but actually it is not tilted, because a raster is always rectangular and the edges of the raster is always aligned with the axis of the coordinate system. For rasters, we say that the location of grid cells are given explicit. This is possible thanks to the alignment of raster. That means that the raster is parallel to the axis of the coordinate system, and because of the cell size. Cell size is also called the spatial resolution and denote the area that the pixel occupy. For instance, here the cell size is 10 by 10 meters. So this cells represents an area on the ground that is 10 by 10 meters large. So what does it mean that location is given explicit? Since in a raster, pixel can only store one value, information of its position needs to be stored explicitly. Often this is done by a header in the file. And this example shows how this is done in Esri's ASCII raster format. The left hand shows the generic format and the right hand shows an example on how the ASCII raster format would be for this particular raster. So first is information about the numbers of columns and rows. So this is a 4 by 4 raster. And then we need to know what we call the Cartesian origin, either the lower left X position for the center or for the corner. So either the corner of this lower left cell or the center of this lower left cell. And in this example, we are using the corner as where we have, after georeferencing, found the Cartesian coordinates. So the corner of the lower left cell is 23 and 25. So the X and Y coordinates. Then the information about the cell size follows, and this is 10. We may have no data values indicated, and then the values in the raster follows. Row 1 having values 36, 35, 33, 31, etc. with row 2 to 4. Now to summarize, the location of grid cells are given explicit, and this is needed because a pixel can only store one value. A georeference raster is aligned with the coordinates axis, and when we know the positions of the lower left corner, when we know the position of the lower left cell, the Cartesian origin, and the cell size, we can determine the coordinates for each pixel size. Now, cell size is a very essential element of the raster data format, and this example shows then the effect that cell size has on the representation of spatial data. On the left side we see a vector representation of a lake, and then we see the same lake represented with raster with the cell size 25 meter, then 100 meter, and then 250 meters. So the numbers of columns and rows are decreasing, and we also see from the shape that the coarser the resolution, of course, the coarser is the representation of the lake. There are some islands which are not visible in the coarser resolution, and also the area becomes more and more inaccurate. So the finest grid, the 25 meter cells, best depicts the location of the polygon and most accurately reflects its area. And it takes almost 100 times as many cells to do so compared to the coarsest grid. In the early days of GIS, of course, resolution and data storage was a big problem, but nowadays having data sets with gigabytes is of less a concern. So key issues to remember from this video: rasters can be image rasters or thematic rasters. Thematic rasters can be discrete or continuous. And discrete rasters can have value attribute table, since the pixel values then are integers. For all kinds of raster, we can only have one value per pixel, and coordinates must therefore be stored explicitly. All rasters are squared, and when they are georeferenced, they are aligned with the axis for the coordinate system.